Hey everybody. So to wrap up our unit on forces and Newton's laws, we have to discuss Newton's third law. Up until this point, we've spent most of our time talking about Newton's first law and Newton's second law. And we've summarized Newton's first law with the concept of inertia. And Newton's second law, we summarize Newton's second law, tells us about acceleration. So Newton's first law deals with things staying the same. Newton's second law deals with things changing. And we talked about, offshoots of Newton's first law, right? We talked about the concept of equilibrium, which is an application of Newton's first law. And then Newton's second law, we said we summarize with this idea, right? The mathematical relationship between force, mass, and acceleration, which we can also rewrite to look like this, right? So we've spent a lot of our time talking about that. This last section, Newton's third law, doesn't necessarily talk about a specific or a single object. It talks about interactions between objects. And where Newton's first law summarized with inertia, and Newton's second law is summarized with acceleration, Newton's third law is summarized by the concept of action-reaction. And most of you have probably heard some version of Newton's third law before, right? For every action, there is an equal and opposite reaction, which is true. But what that means sometimes can be a little confusing. And so in plain person words, right, or maybe explaining a little bit more about how this all works together, when one object exerts a force on a second object, the second object exerts a force back on the first that is equal in magnitude but opposite in direction. So one object applies a force to a second object. That second object pushes back equally as hard, but in the opposite direction. That gives rise to the concept of an action-reaction force, or an action-reaction pair. As I should say, not just force, but forces. Force never comes in solitude. Forces always come in pairs. We can't have one object exerting a force without also feeling a force back on itself, right? We can't say this object pushed that object, or I pushed this chair out of the way. It doesn't work that way. Yes, I pushed the chair, but the chair also pushed me. How hard? Equal in magnitude, but in the opposite direction. So let's take a look at these two girls. Girl in the striped shirt, which I will call striped girl just because it saves me typing, right? Pushes the force on the blue girl. Now you may notice here, right, these girls are they're on rollerblades, right, but make sure that we're being safe. They have the knee pads on, elbow pads, wrist guards, and helmet, right? So you can't accuse them of not demonstrating proper safety techniques, right? That being said, okay, so now that we got that out of the way, striped girl pushes on blue girl, gives her a shove. And if you've ever been ice skating or if you've ever been roller skating before and you've encountered a situation like this, you may know what's going to happen, right? That even though striped girl pushed on blue girl, Newton's third law says that blue girl has to push back on striped girl with exactly the same force but in opposite directions. That being the case, both of them will now accelerate because both of them experience a net force. Now, there may be other forces going on, but if we could just isolate the action-reaction pair, striped girl pushing on blue girl pushing back on striped girl, we will see that both of them end up with unbalanced forces or net forces on them. Those may not be the only forces, but in this case, they are unbalanced. And as a result, acceleration will occur. But because of the idea of equal and opposite, right? Equal in magnitude, opposite in direction, they will experience different accelerations. One will be positive and one will be negative. Now, that's the direction. The magnitude, recall from Newton's second law, right? Now if we examine each girl independently, right? Yes, they exert forces on each other, and yes, they both start accelerating, but once they start accelerating, now Newton's second law applies. So they experience positive and negative acceleration, right, individually, but the magnitude of that acceleration also depends on the mass. They experience the same force, then the mass will determine how much acceleration each one has. To me, it looks like striped girl is a little bit bigger than blue girl. So if two objects experience the same force, the one with greater mass will experience less acceleration. The one with less mass will experience more acceleration. And blue girl doesn't look too sure about this situation, right? She looks a little bit like she's going to maybe throw up. I don't know. But, that's the case. Okay, so they both experience acceleration, but different values or different magnitudes of acceleration due to their different masses. Now, if you have been paying attention, some of these concepts or some of the things that I've been saying might seem contradictory to some things that I've discussed earlier. Way back at the beginning, we talked about Newton's first law, and an application of Newton's first law is equilibrium. And people know about equilibrium, right? The net force acting on an object is zero, its acceleration is zero. And when you read Newton's third law, right, of reaction, there's an equal and opposite reaction. Equal in magnitude, opposite in direction. You may be saying to yourself, wait a minute, forces that are equal in magnitude and opposite in direction should cancel each other out and result in a net force of zero. And if there's a net force of zero, nothing should change. That's equilibrium. So how does anything ever move if these action-reaction pairs are equal in magnitude and opposite in direction? And you wouldn't be the only one who thinks that. It's a very common misconception when we're introducing Newton's third law. Luckily for you, I have this comic strip to explain how that's not the case and how that is a misconception. So, this comic book called Horse Sense, and as you can see here, there's a horse. He's a smart horse because he talks, but he also knows physics, although not as well as he would have hoped. So the farmer says, "Giddy up, pull this cart so we can get going." And then the horse replies to him, "No can do, my friend. For me to pull the cart would be a futile effort." So the horse reasons, knowing Newton's third law. If I pull on the cart will pull back on me. By Newton's third law, the forces are equal and opposite, so they'll cancel. And a zero net force won't get us moving. Which is a reasonable argument. He knows about force, he knows about the vector nature of force, he knows about adding forces to find the net force, right? Sounds pretty similar to everything that we've done so far in this unit. So, let's see where the horse makes his mistake in trying to get out of doing his work. So to do this, let's look at two separate free body diagrams. One for the cart, one for the horse. Separate from each other, right? So we only focus on forces that are acting on each of them individually. So the horse is saying, if he pulls on the cart and applies a force to the cart like this, by Newton's third law, the cart will supply a force back on him. Equal in magnitude, opposite in direction, just like these arrows indicate. Now, the horse, if this was the case, which it is, the horse would get out of work, but not for the reason that he says. If we take a look at these free body diagrams, the cart is experiencing a force to the right. No other forces. Now granted, there's a gravity force, or there's a gravitational force here, right? And then there's a normal force here, right? But we've discussed already that those two cancel each other out because they're equal in magnitude and opposite in direction. And just the same, the horse experiences a gravitational force or a weight force, and he also experiences a normal force from the ground, right? So those cancel each other out. But if we look at each of them individually. The cart experiences 3 forces. 2 of them cancel, but there's nothing to cancel this force out. Even though there is an equal and opposite force on the horse's free body diagram, it can't cancel out a force on the cart. 2 forces that aren't on the same object can't cancel each other. So when the horse pulls the cart pulls the horse. But that force can't cancel out the original force because they are not on the same object. So while action-reaction forces are equal and opposite, they don't cancel each other out because they don't act on the same object. These 2 equal and opposite forces can cancel each other because they're on the same object. But these 2 equal and opposite forces can't cancel each other because they're not on the same object. So now, like I said, the horse could get out of work in this situation because even though those forces don't cancel each other out, because they are equal in magnitude and opposite in direction, but acting on different objects, they will cause each of those objects to accelerate. The cart will start accelerating towards the right, but the horse will start accelerating towards the left. They will eventually run into each other in the middle somewhere. Now, it's probably not exactly the middle because, just looking at this picture, it looks like the cart may have a little more mass than the horse. So the cart would start accelerating to the right with a smaller acceleration value because its mass is less. The horse will start accelerating to the left with a greater acceleration value because of its smaller mass, and they'll meet somewhere not exactly in the middle, closer to where the cart starts. But we're forgetting one object that is involved in this interaction. This clearly cannot be the only thing going on, because if it was, the horse and the cart would run into each other somewhere in the middle, which doesn't happen. So that other object that's involved in that interaction is the earth, not drawn to scale compared to the other objects. So, every time this horse walks, or what we refer to as walking, there is an acceleration. You move forward, right? Generally, your speed increases. Could increase more depending on how fast you want to go, etc. But there's acceleration. That being the case, there needs to be a force on the horse in this direction if he's going to move forward. And it needs to be greater than the force of the cart pulling back on him. So where does that force come from? It comes from the earth. If you want to walk, or if this horse wants to walk, he will apply a force to the earth. You push backwards on the earth, right? That's what we call taking a step. But if you push backwards on the earth, guess what it's going to do? It's going to push forwards on you. Equal in magnitude, opposite in direction. Now, the 2 red arrows are an action-reaction pair. They don't cancel each other out, though, even though they're equal in magnitude and opposite in direction, because they're on different objects. Now, let's focus on the horse by itself. That horse now has 2 forces on him. Technically, if we wanted to start getting real specific, he'd also have a weight force, and he would also have a normal force. All right? So, 4 forces. 2 of them cancel each other out. And there's equilibrium on the y-axis. But if you take a look at the 2 x-axis forces, they are not equal in magnitude, and they are not opposite in direction. Therefore, they don't cancel each other out. Not because they're on different objects, but because they have different magnitude. Just like a Newton's second law problem. So if we could calculate how hard the earth is pushing forward, and then subtract how hard the cart is pulling back, we would figure out the net force on the horse, make him go forward. All right? So, summarize. Action-reaction forces do not cancel each other out because they act on different objects. So our horse, right, mistakenly or misinterprets Newton's third law to say that any forces that are equal and opposite would cancel. Forces that are equal and opposite on the same object cancel, like the weight and the normal force on this horse, but forces that are equal and opposite on two different objects, like these red arrows or these blue arrows, don't cancel each other out. So, then the farmer, having outsmarted a horse, which I don't know, is he proud of that? I'm not sure. If it makes him feel good on the inside, I guess, whatever, right? Then decides, okay, well, hang on, horse, I got you. Don't worry about it, right? Just push backwards on the ground. By Newton's third law, the ground will push forward equally on you. And then I'll just follow along. Like we explained, right? Then the horse will have more than a net force on him in the forward direction. The cart will have a net force in the forward direction. Everybody's accelerating forward now. And then, but that's not good enough. The farmer, not that he's outsmarted the horse, now he's going to take a shot at him and says, hey, this ground is doing a great job, right, pushing forward. And then the horse replies with something that I'm sure some of you have probably thought at this point in time: physics, grumble, physics. So, you know, Newton's third law, right? Yes, it's key to any interaction out there in the universe, but if you don't understand it properly, it can get you in trouble. So just to review, right? Newton's third law is based on the idea of action-reaction forces, right? So Newton3. Newton's third law is based on action-reaction forces. Action-reaction forces are equal in magnitude, opposite in direction, but always act on different objects so they don't cancel each other out. So Newton's first law, inertia. Newton's second law, acceleration. Newton's third law, action-reaction. Newton's first law deals with things staying the same. Newton's second law deals with things changing. Newton's third law deals with how do objects interact with one another.